Good morning, dear students. I'm back. This is a third video on the radioactivity topic. It's a lecture. The course we are studying is Physics 5054. My name is Ferhan Mazher. We are going to study the uses of the radioactivity. And the first use I am going to tell you and we are going to talk about is smoke detectors. The smoke detectors are used in homes, in kitchens, in libraries, in hostels, and in schools, in offices. What they do basically is that the smoke detector is attached with the ceiling, and if, God forbid, something gets catch fire and the smoke starts coming out of that thing, and when the smoke will reach the ceiling, what the smoke detector will do, it will set a alarm, and the alarm will start ringing, and you will know that a fire has started or a smoke has started. So we will learn how this works, and it's very simple. You see, we have two electrodes, and you can see those two electrodes. This is the first electrode, and this is the second electrode. This is connected with the positive terminal, and this electrode is connected with the negative terminal of the battery. And you can see here a battery. So what these, here's a positive electrode, and here we have a negative electrode, and we introduce here radioactive isotope. The radioactive isotope we introduce here is americium. And americium-241 is a radioactive isotope. It gives out alpha particles. And what those alpha particles do, they ionize the air. What they do, they ionize the air, which is connected here, which is present here. So when the alpha particles, they have very strong ionizing power. When they ionize the air between both the electrodes, the positive and the negative ions are created, and the path of the electricity is completed. And until that path is completed, the electricity can flow through from here between the electrodes. Here we have connected a microchip, and you don't need to go into the details of this microchip. The function of this microchip is until the current is flowing between the electrodes. This here we have, here we have that this microchip is also connected with the alarm. If the current continue flowing between these two electrodes, the alarm will remain silent. If by some method this current which is flowing between the electrodes, if by some method this is disrupted, this is disturbed, then what will happen? This chip will send a current to the alarm, and the alarm will start, and it will start producing the sound. So basically what happens when the smoke comes here, the smoke changes the path, the smoke will disturb these ions. When the smoke will disturb these ions, the current cannot flow, and what will happen? This microchip will send signal to the alarm, and the alarm will start ringing. It's very simple. And one very important thing, we use americium, and americium is giving out alpha particles. Why we are not using a source which is giving out beta particles or gamma rays? We can attach the smoke detector with the ceiling, and the alpha particles have very low penetration power. They cannot travel more than 4 or 5 centimeters in air. So when you have attached it with the ceiling, the alpha particles will not be able to penetrate the air. So they will only penetrate 4 or 5 centimeters in the air. So what will happen? They will not reach the people who are in that room. So the people who are living in that room, they will be safe from the alpha particles. If that alpha particles will reach the people, or radiation will reach the people, and that can cause harmful effects on those people. So here you see the number one, a battery. Here we have number one, it's a battery or other power source provides electricity. Number two, americium 241 provide alpha particles that ionize particles in air. Number three, in the absence of smoke, the ions carry current between the positive and the negative electrode. A microchip monitors the flow of current between the electrodes. Under normal conditions, the microchip permits no current to flow through the alarm. The alarm does not sound. If a fire occurs, smoke particles rise up into the detector and interfere with the flow of ions between the electrodes. The microchip senses the drop in current and allows electricity to flow through the alarm circuit, sounding the alarm. So it's very simple. You see, we have using radioactivity, radiation, and by using that radiation, we have made a smoke alarm, and if there will be smoke, the alarm will sound. And before the whole thing gets fired, we will be able to uh, call the fire brigade. So I hope that you have understood. It's smoke alarm. It's simple. Okay. The next thing we use the uses of radioactivity. Another use of radioactivity is that it can be used to check the thickness. It can act as a thickness gauge, thickness gauge. And for example, if you have material, for example, if you are manufacturing the sheets of steel, and you want the steel, the thickness of the steel to be uniform. And what you will do, uh, if for example, this is the sheet of the steel, on one side we will put a source of the beta particles or gamma particles, or gamma rays, I mean, and on the other side of the sheet we put a detector. So you see, you put the material for example, this is the sheet of steel. On one side, I put a source of beta particles or a source of gamma particles, and on the other side, I put a detector. So what that detector will do, it will check how much radiation is passing through that steel, that sheet of steel. So if somewhere the and we have computers which are checking this, and they will check how much radiation is detected by the detector. So the if the reading on the detector changes, for example if the reading on the detector is 400 and continuous is 400, and at some part of the steel sheet the reading changes to 300, it means that the sheet there is thick, is very thin. And for example, if the reading drops to 300, it means that the sheet is thick there. I said thin. It is thick there. So the radiation is not able to pass. And if somewhere the reading increases from 4, it means the sheet there is very thin. So you see, by using the radiation, we are able to keep a check on the material we are manufacturing. We can check its thickness. If the material you are making, for example, if you are manufacturing a paper, or if you are manufacturing sheets which are thin, you can use beta particles. But if the thickness of your sheets which you are preparing or manufacturing, they are thick, then the beta particles might not be able to penetrate through them. So we will use gamma rays. Another very important thing is we don't use alpha particles in this process, because the penetration power of the alpha particle is very low. They cannot pass through the metal sheet, so we don't use them. We use beta particles if the material is thin And the sheets which you are trying to check for thickness, if they are thin, we use the beta particles. If they are thick, then we can use gamma rays also. So it's very simple. I hope you have understood. If a radioisotope is placed on one side of a moving sheet of material and a GM tube on the other, the count rate decreases if the thickness increases. This technique is used to control automatically the thickness of paper, plastic, and metal sheets during manufacture. Because of their range, beta emitters are suitable source for monitoring the thickness of thin sheets, but gamma emitters would be needed for thicker materials. Flaws in a material can be detected in a similar way. The count rate will increase where a flaw is present. Flaw means a crack or there the sheet is very thick. So that's another use of the radioactivity. So let's move to the next use. Here, this is the same use, and you can see here we have this symbol. You can see here we have a radioactive source which will be emitting alpha, beta particles, or I mean gamma rays, and these are the sheets whose quality we are monitoring. And below this, we will have a detector, and that detector is attached with the computer, and the computer is checking. Keep an eye on the thickness of the sheets. So I hope you have understood. Okay, so another use of the radioactivity is as a tracer. So what we do, we put radioactive isotopes into into medicine. We put radioactive tracers into fertilizer, and what actually happens that radioactive isotopes with the medicine or with the fertilizer or with the injections, they go inside the body, and wherever they go, obviously they are radioactive, so they are giving out radiation. For example, if we have a human patient and we inject a radioactive material in the body, so wherever that injection, that fluid will go inside the body, by using a detector outside the body, by using the detector, we are able to tell that that fluid, that liquid has reached where, because the radiation will be coming out of the body, and by using a detector, we can tell to which point or in which organ the medicine has reached. And same way we use it in the fertilizer. What we do, we mix the radioactive isotopes with the fertilizer. And when we mix it with water, and the plant's roots absorb that water, and then by using the detectors, we are able to tell that fertilizer has and the radioactive isotopes have reached to which part of the plant. Another use of tracers is for underground pipes. What we do, for example, if you have underground pipes and you don't know where, if and some leakage is happening, and that piping is underground, so it's very difficult to exactly locate where the leakage is happening. So what we do, we mix the radioactive isotopes with some liquid, and we inject that liquid into that piping. So, and by using a detector from on the top of the ground, we check the radiation levels, and wherever the level of the radiation will go up, it means there the pipe is leaking. So this is the function of tracer. We will read this slide also, and you will be able to understand. The progress of a small amount of a weak radioisotope injected into a system can be traced by a GM tube or other detectors. The method is used in medicine to detect brain tumor and internal bleeding, in agriculture to study the uptake of fertilizers by plants, and in industry to measure fluid flow in pipes. A tracer should be chosen whose half-life matches the time needed for the experiment. the activity of the source is then low after it has been used, and so will not pose an ongoing radiation threat. For medical purposes, where short exposures are preferable, the time needed to transfer the source from the production site to the patient also needs to be considered. So, once again, one very important thing when you use the tracers on a patient. So when you use a tracer on a patient, it's very important the radioactive isotope which you are using, its half-life should not be very, very small, and its half-life should not be very long. The half-life should be, because you see the radioactive isotopes, the patient has eaten or you have injected the radioactive isotopes. So when the radioactive material is inside the body, so that material is giving out radiation. So we don't want that patient to be radioactive for a very long time. The patient should be radioactive for the time only for that time he is in the hospital under the observation of the doctor. So and the half-life of that material, that isotope, that radioactive isotope should be long enough that the doctors can do their diagnose, they can do their observations, and it should be not long. Its half-life should not be very, very long, that the patient might be radioactive for let's say for a week. That will be very harmful for the patient. So it's very important when you will do questions on this topic, you will understand this more and more. I hope that you have understood this thing. Okay, so here we have another important thing is radiotherapy. You know, one very important thing which I forgot is we don't use alpha particles here. You see the alpha particles, the penetration power is very low. So for example, if you injected a radioisotope which is giving off out alpha particles, so if the alpha particles are inside your body, they will be not able to penetrate through the flesh or bone. So the radioactive material will be inside the body, but because if it is giving out alpha particles, the detector will not be able to detect, because you know the alpha particles, they cannot penetrate the flesh. Their penetration power is very, very low. So in the case of if you are using a tracer, we normally use beta particles, because the beta particles or gamma rays, because they are able to pass through the skin and the flesh and the bones, and a detector can be used outside the body to detect where the radioactive isotopes have reached in the human body. So we don't use alpha, any radioactive isotope which is using alpha, which is giving out alpha radiation. So okay, so the radiotherapy, you must have studied in this your electromagnetic spectrum chapter also, that we use gamma rays, and what we use, we focus the gamma rays on that part of the body where we have cancers. And when we focus like gamma rays on a single point, what happens, those cancer cells, they are killed. So gamma rays from strong cobalt radioisotopes are used in the treatment of the cancer. Sterilization, we can use the gamma rays and for killing the bacteria, and these are used to sterilize food. They are also used to sterilize medicine. And an important thing is that that thing will not become radioactive. The food will not become radioactive. Gamma rays are used to sterilize medical instruments by killing bacteria. They are also used to irradiate certain foods, again killing bacteria to preserve the food for longer. They are safe to use as no radioactive material goes into the food. This is not like a tracer in which the radioactive isotopes are injected into the food. No, the food is only subject to the radiation. We do not put the radioactive isotope into the food, okay? So that's why the food will be safe. Archeology is very important, that you must have heard a word, we say carbon dating. With the help of the carbon dating, we are able to, with the help of the carbon dating, we are able to uh, uh, estimate that how old is an object. For example, if you find a piece of cloth, and if you want to find out how old it is, then by carbon dating it, we can find its age. For example, you find a piece of wood. For example, you find a piece of a stone. By using the carbon dating, we can tell what is its age. Normally, what happens if anything which is living, for example, especially plants, wood, when it's living, it's absorbing carbon from the atmosphere. And in the atmosphere, the carbon is of two kinds. The carbon have two isotopes, carbon 14 and carbon 12. Carbon 12 is a normal carbon, but the carbon 14 is radioactive. It's a radioactive isotope of carbon. It gives out radiation. So what happens, till the point the thing is living, it continue absorbing carbon. Once it dies, so what happens, then it no more absorbs carbon from the atmosphere. Then what happens, the carbon 14, which is already absorbed in the body, it starts decaying. And when you get a sample of that thing after many years, so what you can do, you can check the ratio between the carbon 14, carbon 12, how much the carbon which is present there, it has decayed and converted into other material. The scientists, what they do, the archaeologists, what they do, they check how much carbon 14 is left, how much carbon 14 has converted into other material. So from there, and by knowing the half-life of the carbon 14 is 5,700 years. And by knowing the half-life of carbon 14, they are able to predict the age of that sample. A radio isotope of carbon present in the air, carbon 14, is taken in by living plants and trees along with non-radioactive carbon 12. When a tree dies, no fresh carbon is taken in. So as the carbon 14 continues to decay, with a half-life of 5,700 years, the amount of carbon 14 compared with the amount of carbon 12 becomes smaller. Okay, we have already done this sterilization, archaeology. Okay, by measuring the residual radioactivity of carbon containing materials such as wood, linen, or charcoal, the age of the archaeological remains can be estimated within the range of 1,000 to 50,000 years. See worked example on page. The ages of rocks have been estimated in similar way by measuring the ratio of the number of atoms of a radioactive element to those of its decay product in a sample. Okay, so when we use rocks, we don't use carbon, but other radioactive isotopes which are present in them. By observing their amount and how much they have decayed, and by knowing the half-life of the radioactive isotope, we can tell the age of a sample of a rock also. So here we have the year of the construction of this Viking ship has been estimated by radiocarbon technique to be 800 AD. So dangers and the safety, you know, all around us, the radiation is present. We are continually exposed to radiation from a range of sources, both natural, which we call the background, and artificial, as indicated in the figure. So radioactivity in the air, and you can see that there is large portion, there is a huge portion radiation which is present in the air. We have cosmic rays, we have rocks which are giving out radiation, the food is giving out radiation, the medical equipment, the medical procedures, they are giving out radiation. The nuclear power station, some radiation is coming from them, and nuclear bombs, nuclear testing, from there also the radiation is present all around. So you see, we have background radiation. The radiation is present around us all the time. So these are the reasons we have already discussed in our first or second video. Cosmic rays, high energy particles from outer space, are mostly absorbed by the atmosphere and produce radioactivity in the air we breathe. But some reach the Earth's surface. Most of the cosmic high energy particles which are coming from outer space, they do not reach the surface of the Earth. The atmosphere, which is acting like a blanket, it's a safety measurement. It's a safety measure for us. It stops them. Numerous homes, particularly in Scotland, are built from granite rocks that emit radioactive radon gas. This can collect in basements or well insulated rooms if the ventilation is poor. You see, granite, you must have heard this word, granite. It's a stone, it's very beautiful. Its tiles are used, and the granite is radioactive. It gives out radiation. You must have heard, in the New York, we have, I think it's called the Central Station in New York. It's a very big railway station, underground railway station. It's called the Central Station, I think, and it's made of granite. A lot of granite is used, and the radiation level there is very, very high in New York. So wherever the granite is used, and we like granite, it's very beautiful. So people like the granite in their home. They want the walls to be tiled with the granite. And especially in the kitchens, people put granite tiles on the shelves. But it's radioactive. Radioactive potassium 40 is present in food and is absorbed by our bodies. Various radioisotopes are used in certain medical procedures. Radiation is produced in the emission from the nuclear power stations and in fallout from the testing of nuclear bombs. The latter produce strontium isotopes with long half-lives which are absorbed by bone. So we cannot avoid exposure to radiation in small doses, but large doses can be dangerous to our health. The ionizing effect produced by radiation causes damage to cells and tissues in our bodies and can also lead to the mutation of genes, DNA genes. The danger from alpha particles is small unless the source enters the body. But beta and the gamma radiation can cause radiation burns, that is redness and sores on the skin, and delayed effects such as eye cataracts and cancer. Large exposures may lead to radiation sickness and death. The symbol used to warn of the presence of radioactive material is shown in the figure. On the next page we have, this is the symbol on your screen. Wherever the radioactive material is present, is used, a source of radiation is present, you will find this sticker there. The increasing use of radioisotopes in medicine and industry has made it important to find ways of disposing of radioactive waste safely. One method is to enclose the waste in steel containers, which are then buried in concrete bunkers. Possible leakage is a cause of public concern as water supplies could be contaminated, allowing radioactive material to enter the food chain. And I told you that some countries, what they are doing, they are putting their used radioactive material in barrels and they throw it in the sea. And sometimes what they do, the big countries, what they do, they take that radioactive material, put them in the barrels and put them on a ship, and they go into the waters of some poor countries and they dump their radioactive material there. But the good method is you dig tunnels, very deep tunnels, and you put those barrels in those tunnels. But you see the danger is still there. If that barrels, they get leaked and they get mixed with the groundwater, then it can be a problem. You know, wait a minute, let me move it. Okay, the weak sources used at school should also be And this is a safety measure. It's a very important safety measure because in your paper, sometimes this comes of 1 mark, sometimes it comes of 2 marks. They ask you to what are the safety measures against the radioactive materials. Because you see, if you are in a school or if you are in a college or you are in a university and you are working with the radioactive materials, so what safety measures you can take? So the weak sources used at school should always be lifted with the forceps and held away from the eyes and kept in their boxes when not in use. And the boxes, we have the boxes are made of lead and we put always the radioactive material in those boxes because the radiation cannot pass through thick sheet of lead. So we have boxes, we always put the radioactive material in those lead boxes. In industry, sources are handled by long tongues and transported in thick lead containers. Workers are protected by lead and concrete walls and wear and the workers should be wearing the workers should wear radiation dose badges. They wear badges and that keep a check on the amount of radiation they have been exposed to over a period, usually 1 month. The badge contains several windows which allow different types of radiation to fall onto a photographic film. When the film is developed, it is darkest where the exposure to radiation was greatest. So I hope that you have understood till now. So I was telling you that these are the safety measures. I can name you. Use tongs to handle, use forceps, use gloves which have lead lining. We wear aprons which have lead lining, and we use gloves which have lead lining, and we wear badges, and those badges have photographic films in them, and they have different layers, different windows on them, which have different materials on them. So for example, if you are exposed to alpha particles, if you are exposed to beta particle, if you are exposed to gamma rays, and by observing those photographic badges, the the scientists are able to tell that how much exposure you have to the radiation. Okay, Ji? Okay, here we come to another very important uh, aspect. This is called, you must have seen this, you must have seen this equation. E is equals to mc square. This equation this equation is given by Einstein, and it's very important in your physics course. It's important. You see, it's a very unique idea, and the idea is this: that till now we have been telling you that the energy cannot be created nor destroyed, but it can change from one form of energy to another form of energy. We have also been telling you that the mass cannot be created nor destroyed. Mass is always conserved. The energy is also conserved. But this equation says that the mass can be converted into energy and the energy can be converted into mass. If you convert mass, if you convert a very small amount of mass into energy, it's not a chemical reaction. We're not talking about a chemical reaction. It's a nuclear reaction in which if a little amount of mass, a fraction of a gram, if it converts into energy, huge amount of energy will be produced. This equation E equals to mc square. Here E is the energy, m is the mass, and c is the speed of light. Speed of light is 3 expo 8 meter per second. E is the energy, m is the mass. If m converts into energy, E energy will be produced. So you see, it's an idea that the mass can be converted into energy and energy can be converted into mass, and the people use If you might have heard, sometimes people say that mass is actually a lot of concentrated form of energy. So this is that idea. So sometimes this comes in paper, especially in MCQs it comes. Einstein predicted that if the energy of a body changes by an amount E, its mass changes by an amount M given by the equation and do not happen in the chemical reactions. E is equals to MC. This happens in nuclear reactions. E is equals to MC square, where C is the speed of light, 3 into 10 raised to power 8 meter per second, 3 expo 8 meter per second. The implication is that any reaction in which there is a decrease of mass, the mass which changes is called mass defect. The mass which disappears, which converts into energy, that is called mass defect, is a source of energy. The energy and mass changes in physical and chemical changes are very small. Those in some nuclear reactions, those in some nuclear reaction. Such as radioactive decay are millions of times greater. It appears that mass matter is a very concentrated form of energy. Okay. So another very important thing is the fission. So try examination point of view, it is very important. Fission, what does the fission mean? In the fission, what happens? We have a large nucleus and we bombard it with different particles. For example, we bombard it with a neutron. So what happened? We have a large nucleus and we bombard it with a neutron. We accelerate a neutron in a particle accelerator, and then we bombard that neutron with the large nucleus, and we call it the parent nucleus. And what happens? That nucleus breaks. It's not chemical reaction, it's a nuclear reaction. You see, what happened? We bombard a neutron on the nucleus of a large nucleus, and that nucleus breaks. And when that nucleus breaks, it converts into 2 or 3 smaller nuclei. You see, in the fission, what is happening? We have a larger nucleus. We bombarded it with a neutron, and what happened? It breaks into smaller nuclei. We call them daughter nuclei. And by this, some of the mass defect happens, and some other particles are also produced, and smaller nuclei are produced. And due to the mass defect, large amount of energy is produced. Large amount of energy is produced, and that energy can be used also. The heavy metal uranium is a mixture of isotope of uranium 92 235, called uranium 235, is the most important. Some atoms of this isotope decay quite naturally, emitting high speed neutrons. If one of these hits the nucleus of a neighboring uranium 235 atom, being uncharged, the neutron is not repelled by the nucleus. This may break fission of the nucleus into 2 newly equal radioactive nuclei, often of barium and krypton, with the production of 2 or 3 more neutrons. So you see what is happening. We have a big uranium nucleus, and we have a neutron. And neutron is neutral, so it is not repelled by the nucleus, which is positive. So what happens? A high-speed neutron, if it strikes, it's collide with the nucleus of uranium, it breaks. And when it breaks, it makes 2 smaller nuclei, barium and krypton. And when they are produced by the breakage of that larger nucleus, 2 more neutrons are produced. And when those 2 neutrons are produced and they are also at very high speed, they can go and they can do the fission of 2 more uranium nuclei. So it's kind of self-sustained reaction. So you only need to start it. Once you started it, so you see, you take a neutron, you bombard it on a nucleus of a uranium atom, And when that will break, two more neutrons will be produced, and they will be at very high speed, and they will move and they will do the fusion of the neighboring uranium nuclei, and then this process will go on. And so it's a very dangerous reaction. The mass defect is large and appears mostly as kinetic energy of the fusion fragments. These fly apart at greater speed. Let me adjust my so you can see it clearly. So colliding with the surrounding atoms and raising their average kinetic energy, that is their temperature, so producing heat. If the fusion neutrons split other uranium-235 nuclei, a chain reaction is set up. In practice, some fusion neutrons are lost by escaping from the surface of the uranium before this happens. The ratio of those causing fusion to those escaping increase as the mass of uranium-235 increases. This must exceed a certain critical value to sustain the chain reactions. A certain amount of uranium is required. If you do not have that uranium, that amount of uranium, so that then this will be not self-sustained. So here you see we have a neutron, and what will happen that this neutron, when it will strike this uranium nucleus will be broken, and it will go into two small pieces. And one will be the barium, other one will be the krypton. So the nucleus is broken, it's fission broken. And with that, two, two more neutrons are produced. When this breaks, two more neutrons are produced. So those two neutrons will do the fusion of two more uranium, and then the four neutrons will be produced, and they can do the fusion of four. And from four, you will have 8, and from 8 you will have 16. From 16, you will have 32, and from 32 it will go to 64. So see, if you have a certain amount of uranium, this process can go on. So this is called a chain reaction. If this happens, it's called a bomb. So here we have a simple diagram of a nuclear reactor. It's a very, very, very simple diagram of a nuclear reactor. So try to understand what is a nuclear reactor. It's very basic, very, very basic thing which I'm trying to tell you. Okay, so we have in the nuclear reactor, we are doing fission reaction. In the nuclear reactors, the reactors which are producing electricity, and for power generation, we are using the nuclear reactors. And in those nuclear reactors, the fuel is uranium. And what the process we do there? We do the fission of uranium rods, and we do the fission. We just studied the fission of the uranium, and but we control it. In the last slide, I told you that the chain reaction starts, and if you do not control it, it will get out of your hand. It will be like a bomb. So the same process we are doing here, but we are controlling the neutrons. When the fission of the first uranium atom takes place, nucleus takes place, the neutrons are produced. If you are able to control those neutrons, then you can control this nuclear fission, and you can because a lot of heat is produced when this reaction, when the nuclear fission, when this nuclear reaction takes place, when the nuclear fission of uranium takes place, lot of heat is produced, lot of energy is produced. And if you can control it, you can use it to produce electricity, you can use it to produce use it for good purposes. For that purpose, you see, we have here you can see in the green color, you can see these are the uranium rods. So that is the fuel for the uranium rods are basically the fuel for the nuclear reactor. And this gray color thing, this is graphite. And inside the graphite, between each rod, we have graphite. and in that graphite we have boron rods, and these boron rods, they can go in and they can come out. So for example, now you see the boron rods are lifted upward, so this lower portion of the these uranium rods, they are exposed for the fusion reaction. And but this upper portion, the upper portion which is between the boron rods actually absorb the neutrons which are produced. So these upper portions of the uranium which are between the boron rods, their fusion cannot take place. So by the help of the boron rods, by putting them downward or moving them upward, we are able to control the fusion reaction of the uranium. So when this is happening, a lot of heat is produced. And what we do, we take a gas which is very cold and we pump it in here. And from here, the gas gets very hot, and from here it goes out. And from here it's coming back. And here we have inside the pipes, this blue pipe, you see we have water, and it's going. So the cold water is coming from here, and from here so much that gas was so hot, so the water inside this pipe, that turns into steam, and from here that steam goes out, and the steam is used to turn the turbine, and that turbine can then turn the generator, the rotator of the generator, and the electricity is produced. So this is how the atomic nuclear reactor works. And the fuel for the nuclear reactor is uranium. And what process is taking place there? Nuclear fusion, in which the uranium, a large nucleus is broken down into smaller nuclei, and large amount of energy is produced. I hope you have understood. So nuclear reactor, in the nuclear power station, heat from a nuclear reactor produces the steam for the turbines. Figure which we saw is a simplified diagram of one type of reactor. The chain reaction occurs at a steady rate, which is controlled by inserting or withdrawing neutron absorbing rods of boron among the uranium rods. The graphite core is called the moderator and slows down the fusion neutrons. Fusion of uranium-235 occurs more readily with slow than with fast neutrons. Carbon dioxide gas is pumped through the core and carries off heat to the heat exchanger, where steam is produced. The concrete shield gives workers protection from gamma rays and escaping neutrons. That whole thing is covered, that whole plant is covered in the very thick wall of concrete. The concrete shields gives workers protection from gamma rays and escaping neutrons. The radioactive fusion fragments must be removed periodically if the nuclear fuel is to be used efficiently. In an atomic bomb, so when we make the atomic bomb, we do not control this fusion reaction. We just start it and we let it go. In an atomic bomb, an increasing uncontrolled chain reaction occurs when two pieces of uranium-235 come together and exceed the critical mass. Okay, now we have another reaction that is called fusion. The fusion is opposite to fission. In the fusion, we have a large nucleus and it breaks and make three smaller nuclei. But in fusion, the opposite happens. What happens? We have smaller nuclei and we bring them close. And they fuse with each other and they make a larger nucleus. This is called fusion. When this happens, immense amount of energy is produced. And the fusion is happening on the stars, on the sun. You see, it's very important that when you try to bring two nuclei together, the nucleus has positive charge. For example, this is nucleus A, this is nucleus B. It is positively charged, it is positively charged. When you try to bring close, they both are positively charged. Both nucleus have protons in them, they are positively charged. So they will repel each other. So when you try to bring close to each other, these two nuclei, they will repel each other. So you have to make their kinetic energy very high. So much kinetic energy that they can overcome that repulsion. And when they collide with each other, they fuse into each other, they make a larger nucleus. For example, if we have hydrogen and hydrogen nuclei, when they fuse with each other, we have a smaller hydrogen nucleus, we have another smaller hydrogen nucleus. They come close, they fuse, they make a large nucleus, they make helium. This is called fusion. And this is happening on the sun, this is happening on the stars. This reaction, the fusion reaction, is the source of energy on the stars and on the suns. If light nuclei join together to make heavier ones, this can also lead to a loss of mass and as a result, the release of energy. Such a reaction has been achieved in the hydrogen bomb. At present, research is being done on the controlled fusion of isotopes of hydrogen, deuterium and tritium. Deuterium and tritium, they are the isotopes of hydrogen. You see the, to give helium. So here you see we have, deuterium and this is the tritium and they join together, they make helium and a neutron is given out and lot of beyond your imagination, the energy is given out. Fusion can only occur if the reacting nuclei have enough energy to overcome their mutual electrostatic repulsion. You know that both the nuclei, when you try to bring them close to each other, because both of them are positively charged, so they repel each other. So they have the electrostatic force of repulsion, which is very strong. So they should have enough energy to overcome that electrostatic repulsion between them. This can happen if they are raised to a very high temperature, over 100 million degrees centigrade, so that they collide at very high speeds. If fusion occurs, the energy released is enough to keep the reaction going. Since heat is required, it is called thermonuclear fusion. The source of the sun's energy is nuclear fusion. The temperature in the sun is high enough for the conversion of hydrogen into helium to occur in a sequence of thermonuclear fusion reactions known as hydrogen burning sequence. So here we have a reaction. So you can you don't need to memorize it, and you can have a look at here, and you can see that these hydrogens, they are at the end converting into helium nucleus, and they produce lot of energy. Each of these fusion reactions results in a loss of mass and a release of energy. Overall, tremendous amount of energies are created that help to maintain the very high temperature of the sun. This concept that what is happening on the sun, fusion is happening on the sun, in every second paper this concept is coming in the MCQs. So by this, my dear students, we have reached the end of this chapter. This was the third video on radioactivity, and this third video was on the uses of the radioactivity. I hope that these lectures are helpful to you, and I have tried to do the detailed description of everything which is required in your course, and I hope that it will benefit you all. So thank you very much, everybody, and have a good day, and God bless you all. Thank you very much.